Thanks for joining me. Today we're going to be going through ionic bonding. Real quickly, you see on the screen it says we're going to just try to understand how compounds are made due to ions. So we're kind of where we're headed in terms of what we need to be looking at. But we're going to take a few steps before we end up getting there. So some of this is going to be largely a review. Really our new content is, again, predicting the charges of elements when they become ions. We've touched on this already, so this shouldn't be anything brand new. A little bit of new vocabulary, which is called a cation, anion, and then we're going to go over valence and oxidation numbers again. So let's remember that on the periodic table, all the elements except noble gases tend to want to gain or lose electrons. So we've got our noble gas column on the periodic table. We don't really have to worry about them gaining or losing electrons because they're perfectly happy the way that they are. Everything else, however, needs to gain or lose electrons. So if we look at our pictures that we have, the images that we've got on the screen right here, there's a couple of atoms with Bohr models on them. The one on the bottom left is potassium, and you'll see that it's got one electron in its outside shell. So it does not have a full outside shell, and there's some energy issues with that it would like to fix, and in order to do that, it needs to probably end up getting rid of an electron. If we come over here and look on at the upper right-hand corner, we see krypton, which is a noble gas. It does have 8 electrons in its outside shell, and it's basically what we think of as if it were a person, a happy atom. It's got all the electrons in its outside shell. The idea is that if you want to think of it, it's kind of like these things want to be like a noble gas. Obviously, they're atoms, so they're not necessarily want to actually be like something, but we can think of them that way. So, as an example, going back to potassium, it's got the 1 electron that's out here on the outside shell. If it could get rid of it, then effectively this whole outside shell goes away, and then this becomes the outside shell. My marker's not working perfectly. And we see that the next shell on the inside already has 8 electrons. So if we can get rid of this one, effectively potassium has an outside shell that would be just like krypton, and that would be kind of like being a noble gas. So that's what happens with most of our elements in reality is they end up getting rid of some of these electrons. Or they gain electrons to become like a noble gas. And it depends on where they are on the periodic table as to whether they gain or lose. But again, it's very predictable for us. So they want to have a full or a stable outer shell. They're going to gain or lose electrons to do that. And then the way that our pattern again goes is that the metals, these things over here on the left-hand side, even in hydrogen, even though it's not a metal, these are the things that are going to tend to lose their electrons because they don't have very many in the outside shell. They've either got 1, 2, or 3 in general. And so it's easier, if you think about this as a board game, it's easier for them to move backwards to get back to the noble gas column. Potassium, as an example, if we look at potassium on the periodic table, potassium's right here. So the easiest thing for it to do is, again, it gets rid of that electron. So now it doesn't have 19 electrons. It's got 18 electrons, just like argon would have. So what happens with it? It loses that electron. So these guys over here end up losing their electrons. Those over here do the opposite because they want to get into the noble gas column. They need to gain electrons to be able to do that. So again, we've got very predictable patterns. And the more we understand our periodic table, the more we can just remember our patterns. So metals lose electrons. I'll put the letter L up there because I can use my hand to help me remember that. My left hand in particular, if I look at the periodic table and put it on the left-hand side, that helps me to remember that the left side ends up losing electrons. A couple of vocabulary words we have with this. Positively charged ions have their own special word called a cation. A lot of people want to say cation, but it's a cation. Which one? You got the little picture of the cat up here. Anions, got a little picture of an onion, which is close to the spelling of an anion. But usually if we put A or AN in front of something, it means not, and that's where the negative comes from with this. Metals make cations, non-metals make anions. And so we can start grouping a few things together, right? So we have metals. Metals are the cations. Cations end up losing electrons. And if you lose a negative, then this ends up resulting in having a positive charge. So all these things tend to go together. I can make another column over here for nonmetals, and it would just be the opposite, right? So instead of a metal, I would have a nonmetal. Instead of a cation, I have an anion. Instead of losing electrons, they gain electrons. and instead of becoming positive, they would end up becoming negative. So we will use those words, cation and anion. We'll probably see those on assessments as well. Cat is positive, anions are negative. And this leads us to oxidation numbers, which we've gone over before. Again, we've got a pattern on the periodic table of the oxidation numbers. You'll notice that we've got pluses and minuses. Again, the metals on the left-hand side end up being positive. We've got kind of a dividing column here with carbon. And then once we get past carbon, things start turning negative because they're going to be gaining their electrons. They're going to be becoming negative. So the oxidation number, again, by definition, what an oxidation number is, it's not a counting number, it's a charge. It's the charge of an ion after it gains or loses an electron. And again, we have this pattern on the periodic table that we can look at. And it's associated with the number of valence electrons. So again, everything in the first column has one valence electron. It loses that valence electron, which ends up making it have a +1 charge because it's got one less electron now. So all the numbers you see on this picture have to do with what is its charge after it either has its valence shell completely lost or filled up. Notice transition metals are not colored in because they basically don't have a pattern, and we need to look those up on a chart. And so from this point on, the reason we need to know the oxidation numbers is because that's going to help us to know how the ions are going to combine together, because they don't like to have a charge, even though they don't like to have a empty shell. The problem with getting an empty shell. All right, so if we know the oxidation numbers, that's going to let us know how elements are going to be able to combine to form compounds, which is kind of where we're headed to in our course sequence. In order to get an ionic bond, we have to have a metal and a nonmetal, because metals become positive and nonmetals become negative. So we're never going to have metals connect with metals in an ionic bond, and we're never going to have nonmetals connect with nonmetals, because pluses don't attract pluses and minuses don't attract minuses. When we have an ionic bond, we've got to have a metal and a nonmetal. So we have a cation and an anion that are going to attract, and kind of the goal of this is to get everything back to a neutral charge. When we're writing out the charges of the elements, or excuse me, the ions, again, we use what's called a superscript, and we indicate the charge with the superscript. So chlorine ends up having a -1 because it's got a -1 oxidation number. That means it's going to have gained an electron, and we would indicate that with a little -1 up at the top. Magnesium, which is a metal in column 2, is an alkaline earth metal. It's going to lose 2 electrons, and when it loses 2 electrons, it's going to have a charge of +2, and we would indicate it as such. So with this being a metal and a nonmetal, they would have attraction to one another. But the problem with chlorine and magnesium is, you notice that their numbers wouldn't exactly neutralize or cancel each other out. Chlorine is a -1 and magnesium is a -2. So what we'll end up seeing in a later video is, in order for these to kind of neutralize each other, I'm going to need 2 of those to kind of cancel out the one magnesium we have over there. And then, so we can use these numbers again to indicate ratios and help us to figure out how many of each one we would need in order for them to cancel out. Sometimes they cancel out perfectly. For example, sodium and chlorine. Sodium becomes +1, chlorine becomes -1. You just need one of each. That's how sodium chloride gets together, which is salt. And we would just write the formula as such for NaCl. Some things are a little bit more complicated, of course, and we will figure out how to do all these things. So this is going to lead us to writing formulas and giving names to ionic compounds, and that's kind of what we'll head into our next video. So in summary, most atoms are going to be able to form ions except for the noble gases. We use oxidation numbers, which are the pluses and minuses, to indicate the charge of the ion once it gains or loses electrons. And we're going to be able to eventually use these oxidation numbers then to predict how ions will combine into ionic compounds. And we're going to be able to write formulas and names for things such as sodium chloride and magnesium chloride and magnesium fluoride and so forth, and to write their proper formulas. All right, thanks for being here.